Welcome back to my YouTube channel, Shear Analysis. What we have here is a beam that contains a UDL, which is short for uniformly distributed load. In this video, we would calculate for support reactions, shear force, bending moment, and most importantly, maximum bending moment. This is a little bit more complicated than that of a beam, which contains only point load. So you would have to pay more attention. Now we'll start by calculating the support reactions. We have RA. The next force is a negative force, which is -5. The next is a UDL, so you have -10 times its span, which is 4 meters, -5 plus RB is equal to 0. Summation of all the forces acting on a beam equal to 0. So you have RA plus RB is equal to, we're collecting like terms here, so you have 5 plus 40 plus 5. So you have 10 times 4 is 440, so just so you know. So you have RA plus RB is equal to 50 kilonewton. So we take this as equation 1. Take a moment about point B, which is at support RB. We'll have RA. This support will move in a clockwise direction since it is acting towards B, which makes it a positive one. And it has a distance of 8 meters, which is 242, so times 8. Next is the 5 kilonewton. Now this acts in an anti-clockwise direction, which is a negative one. So we would have a negative sign and next. So have -5 times its distance, which is 4 plus 2, which is 6. Next is a UDL, which will firstly convert to point load, which is -10 times its span, which is 4 meters. Now that it has been converted to a point load, it will act at the middle of its span, which will divide its span into 2 equal parts, 2 meters and 2 meters. So multiply by the distance to B, which is now 4 meters. So we have times 4. The next is a 5 kilonewton acting anti-clockwise also, which is -5 times 2 equals to 0. So resolving this, we'll have 8RA minus 30 minus 160 minus 10 is equal to 0. So collecting like terms, we have 8RA is equal to, we sum 30 plus 160 plus 10. So you have 8RA is equal to 200. So you have RA equal to 200 divided by 8. We have RA is equal to 25 kilonewton. Now we'll put this back into equation 1. So we have 25 plus RB is equal to 50. So collecting like terms, we have RB is equal to 50 minus 25 is equal to 25 kilonewton. Hence, RA is equal to RB, which is equal to 25 kilonewton. It is safe to say that this beam is symmetrical. Now we've successfully obtained our values for the support reactions at point A and at point B. I hope you've learned something from these few steps. If you haven't, then you have to stick with me, because the next step is for obtaining the values for the shear force. Now I have to just wipe this off so we'd have like enough space to calculate for the shear force. I just write down the values for RA and RB so we don't forget, which is 25 kilonewton. Now calculating for the shear force. First thing we need to do is to label the spans. We already have point A and point B. Now we need to label C and D. Well, we're having a little bit of, so I just wipe this off. So I'm going to write down here C, and here at this point we have D. So the first thing to do is to calculate for the shear force at A. Now the shear force at A is simply the support at A, or rather the force at A, which is RA, is equal to 25 kilonewton. Now the next span is span C, so we'll calculate for shear force at C, which is equal to RA. The next one is negative, so it's a minus sign, so minus 5. We have RA as 25, so 25 minus 5 will give us 20 kilonewton. Considering the UDL, we have to take into cognizance the shear force between C to D. So that's what we're calculating at. So shear force at C to D span, we bring down 20 kilonewton minus, firstly, we need to convert it to a point load, which is 10 times 4. So we have 20 minus 40, which will give us minus 20 kilonewton. Something very significant happened at this point. We'll come back to it later. So we have shear force at D, which is the next one. We have shear force at D. We bring down the previous value, which is minus 20. Then at D, we have a force of 5 kilonewton, which is acting downwards, which is minus 5. So we have minus 25 kilonewton. Now take note, shear force at B is always minus the value gotten at B. So we'll have minus, minus RB, which is equal to minus 25 kilonewton. Now, these are the values we've obtained for shear force, and we're going to move next to bending moment, but I'll just write it down here so I can wipe this off so we'd have like enough space to calculate for bending moment. So I'm just going to write down the values here. D is C to D is equal to minus 20 kilonewton. At D is equal to minus 25, and at B remains the same, which is equal to minus 25 kilonewton. Wiping this off now. So we're moving forward to bending moment. So for a simply supported beam, bending moment at A and at B is always equal to 0. Now next is for us to get the bending moment at C. But just going to quickly divide this so we know our boundaries. So bending moment at C. To determine this, we have to take from the beginning of the beam to the point C. So we have RA times whatever distance, because bending moment is force times distance. So we have the distance from RA to C is 2 meters, so we have RA times 2. We know our RA to be 25, so we have 25 times 2, which will give us 50 kilonewton meter. That's the unit for bending moment. Now the next to go is to get your bending moment at D. Now we do the same. We can start from the beginning of the beam to D, or we can even go from the right hand side, but I'm going to go from the left hand side this time. So we have RA times the distance from A to D would be 6 meters, which is 4 plus 2. The next is an anti-clockwise moment, which is 5 times this distance, which is 4 meters. The next is a UDL, which is 10, converting into point load multiplied by 4. As the point load is going to act at the middle, so the distance from the middle to D is 2 meters. I hope you understand that. So we have 25 times 6, which is the value for RA, minus 5 times 4, minus 10 times 4 times 2. So resolving this, we have 150 minus 20 minus 80. So we have bending moment at D to be a 50 kilonewton meter. So we've successfully gotten our bending moment for the point A, C, D, and B. The next thing we're about to go into is to calculate for the maximum bending moment. I'm excited. So that'll be like the fun part of this lesson, the maximum bending moment, because it's different from when you have a beam with only point loads. It's a different way of calculating the maximum bending moment. So I've just written down the value for the bending moments at C and at D, so we don't forget. Now at A and B is 0 kilonewton meter, everybody knows. So maximum bending moment. Now for maximum bending moment occurs where the shear force is equal to 0. Now who can guess why the shear force is equal to 0? Remember when I told you that at point C to D something significant just happened there? The value of shear force just moved from positive to negative. Now to move from positive to negative, it must have crossed the 0 mark. So what we have, our maximum bending moment is from where it crossed from positive to negative, which is at point C to D. So I'm just going to write it down. Maximum bending moment occurs between C to D. So we have to calculate for maximum bending moment there. So I'd have to draw a section of this beam, which is going to end at, I'm going to cut it at this point. So we're going to draw the diagram now, so we can be able to calculate for our maximum bending moment. So we have support reaction A all through. So we're cutting it here. This is represent the shear force, and this is the bending moment, say mx. And oh no, that's not the right position. F stands for shear force, so this is RA. Now we have our 5 kilonewton, and we have our UDL as well, 10 kilonewton per meter. And we have 2 meters, and we do not know this distance at which we cut it, so we'll label it X. So now that we have all this, the first thing to look for is the shear force, because at this point we assume the shear force to be 0. So looking for the shear force, so we're going to get the shear force equation. Now remember, shear force is the summation of all the vertical forces acting on the beam, and so we have RA, which is a positive force, minus 5, which is negative, and then we have the UDL, which we have to convert to point load, which is minus 10 times its span, which is x, thus we have 10x, and then minus the shear force, which is there. Now we remember that shear force is equal to 0, so we have RA, which is 25 minus 5 minus 10x minus 0. So when we resolve this, we have 20 minus 10x is equal to 0. When we call it like terms, we'll have minus 10x is equal to minus 20, sorry. So we cancel out the minus sign. So we have x is equal to 20 over 2. So we have x is equal to 2 meters. That means the the distance at which we have the maximum bending moment is 2 meters away from point C, which is also like the middle of C to D. So we now have our x as 2 meters, which we are going to use to calculate for the maximum bending moment. Now we're going to derive the equation for the maximum bending moment also. So we have RA, which is acting at a clockwise moment till this point. We have RA times the distance, which is now 2 plus x. The next is a 5 kilonewton, which is an anti-clockwise moment, negative. So you have minus 5 times the distance, which is x. And then the next is the UDL, which you first have to convert to point load, which is 10 times x. Then it will act at the middle, dividing the span into 2 equal parts. So you have x over 2. So 10 times x over 2. And then you have the moment, which is a negative 1. So you have minus m is equal to 0. Wow, so this is the equation for bending moment. Now, resolving this, we have to take m to the other side. So we have m is equal to RA, which is 25 times, open bracket 2. Now, remember x is 2, so we have 2 plus 2. Substituting the value for x, so we have minus 5 times 2 minus 10 times 2 over 2. Yeah, so resolving this whole thing, we have m is equal to 25 times 4 minus 5 times 2 minus 10 times 2 times 1. So we have m is equal to 100 minus 10 minus 20. So we have m is equal to 70 kilonewton meter. So this is the value for the maximum bending moment that occurred in this beam. So having gotten all these values, we have to also write this down, and the next stage is to draw the shear force and bending moment diagram. So that is like the final stage for this question. I hope like this is not too long. But you can also drop like you can also state your video ideas, like what you want me to do, the next video you'd like to see, in the comment section. And if you are a new viewer, please don't forget to subscribe to my channel and like this content if you like what you've seen so far. So I'm just going to transfer these values from this side to the other side of the board, because I want to draw the shear force diagram directly beneath the question. Yeah, so we'll have shear force at C to D as minus 20. If we can remember, we have D to be minus 25, and we have B to be also minus 25. Then we draw a line just to demarcate between shear force and bending moment. So I have bend moment at A and B to be equal to 0, at C to be 50 kilonewton meter, at D to be the same 50 kilonewton meter, and we have our maximum bending moment to be 70 kilonewton meter, which occurs at a distance 2 meters from C. Now we're going to draw dotted lines just to mark out where our shear force and bending moment diagrams will be. So this marks point A, this marks point C, this line marks point D, and this other line marks points RB. So we'll draw a straight line. This is for shear force. Now we have to label the points A, B, C, and D. Now we start with shear force at A, which is 25 kilonewton, which is about this point. We assume here to be like a 25 mark. Then it acts the same until it gets to the point C, where another force is acting on it to change the force. So then we have 20 kilonewton at C. So it's also at this point mark. It acts. Now for a UDL, we do not use straight lines. We use slant lines or inclined lines, as you would call it. So now this is the point where shear force crosses from positive to negative. So we're going to draw a slant line at a mark minus 20, which is at D, and it goes like this. So here, so after that we have a minus 25 at point D, which will go down to somewhere here. It acts the same until it gets to B. B, which is also a minus 25, will come like this. So this is the shear force diagram. This side is positive, this side is negative. This is the shear force diagram for this particular question. I'll move on to draw the bending moment diagram. Also would mark our point A, our point B, our C, and then D. Now remember, the maximum bending moment occurs at a point where shear force is equal to 0. And now that is the point where the inclined line cuts the horizontal line of the shear force. So for shear force, I already said that before, we have inclined lines. I'm just going to write it out for you. And then inclined lines for UDL. And then for bending moment, for a UDL, we use curved lines. Now at this point where we're going to mark our A and B to be 0 kilonewton, our C and D to be 50 and 50. Of course, they're going to be like at the same mark. Then we're going to mark our maximum bending moments, which is at this point. At this point, shear force is equal to 0. So we just trace it down. And then we know our maximum bending moment lies around this line. So we have a 70 kilonewton meter. And then we're just going to, join these lines. For the point loads, we use inclined lines. But for the UDL, we're going to use a curved line. So from A to C, we have something like this. Then from here, we'll have a curve, which is going to run through to D. So it's going to be like this. Oof, permits my curve. And then lastly, we draw a an inclined line to B. So this is the bending moment diagram for this question. It is a positive one. So yeah, that's all for bending moments and shear force diagram. Easy, right? So please like this video and share. Thank you.